Good morning, everyone. A very warm welcome to you all to today's PVTECH webinar in association with Huasun Energy. I'm Ben Willis, consultant editor at Solar Media. We publish PVTECH alongside our other industry-leading news channels, Energy Storage News and Solar Power Portal. Today, we're going to learn more about the reliability and durability of heterojunction PV modules. Heterojunction technology, or HJT, has been in use for well over 20 years, but until relatively recently was regarded as something of a premium product whose natural niche was the residential rooftop market. However, with the growing dominance of N-type technology, cell types such as heterojunction and TOPCon have also dramatically increased their reach, with market research firm InfoLink predicting that they will jointly account for 70% of cell shipments this year, up from just 25% last year. In the case of heterojunction technology specifically, global manufacturing capacity is expected to approach 70 gigawatts by the end of 2024, according to InfoLink. This is down largely to the falling cost curve for HJT and other improvements such as increased bifaciality, which have enabled HJT modules to reach a levelized cost of energy that makes them a viable choice for larger utility scale projects. But as the scale at which modules are deployed increases, so too do considerations around durability and reliability. Installing a handful of modules on a household rooftop is one thing, but when a project enters multi-gigawatt territory, confidence on the part of the investors that those modules will collectively perform as expected over the project lifetime becomes a key consideration. The purpose of today's webinar is to take a closer look at how HJT modules perform in real-world situations. Huasun is one of the leading volume producers of HJT modules today, and its head of business for Europe, Christian Combs, will walk us through some of the factors that most influence the performance over time of modules made with HJT cells. We'll learn about the most common degradation and failure mechanisms for HJT cells and modules, and also what mitigation measures can be taken to increase their lifetime and yield. After Christian has given his presentation, as is standard practice in our webinars, we'll be opening the floor to questions. This interactive element of the webinar is your chance to go into greater detail on today's topic. So please submit any questions you may have using the questions tab at the bottom of your screen, and we will do our best to get to them. So without further ado, I'd like to hand over to Christian. Christian, the floor is yours.
Thank you, Ben, and good morning, everyone. Good afternoon, good evening, if it's your case. Let's get on with the presentation. Today, I want to divide the presentation basically in two blocks. First, I will show the heterojunction to remind you how it is made, this kind of cell and module. And then we will go in the bigger part into the degradation modes and then a little outlook. So those of you who have been a long time in the industry and those of you who are new have very different starting points of the knowledge. So let's put everybody at the same level. Heterojunction is called heterojunction with the word hetero inside because it uses two different materials for the P and the N part of the PN junction. We use in heterojunction a crystalline wafer, and then we use for the other part of the PN junction, this is the N type, is the wafer. The P type is made with amorphous silicon or microcrystalline silicon, which is deposited on top of that wafer. That is the source of the name of heterojunction. All other technologies that are mainstream right now, such as PERC or TOPCon, they do the PN junction inside of the crystalline wafer. You see here a structure where I'm listing, oh, the presentation is somehow gone. I hope it's better now. We see here a structure where there is amorphous silicon. I don't know everybody, but sometimes somebody is clicking on the screen and moving things around. I'm not sure why that's happening.
I don't know who
please
that is.
stop. Sorry for the technical difficulties, everyone. When we look in more detail at the structure, I want to point out to some very small details that are useful. The first one is that we have amorphous silicon next to the wafer. This is the main passivation of the edge of the wafer, and this is what distinguishes heterojunction from everything else. But this is an intrinsic layer. This means it's not dotted, it's not positive or negative, and then we have successive layers of microcrystalline silicon until we reach the TCO, transparent conductive oxide, which is a conductive layer at the top, is the anti-reflection layer as well, and then the fingers where the connection to the other cells are happening. This will come in handy as an information later because the devil is in the details. Now I want to explain you how our modules are made. We use in Huasun, and most of the manufacturers who do heterojunction, only glass modules. This is done in order to protect the cells best against humidity and any other contaminant going into the laminate. So what we do specifically is we have as well something called sealing. We use PIB, which is a type of plastic material, in order to completely seal all of the edges. We use as encapsulant an encapsulant that is based on EVA or EPE that has additives that help control the amount of UV irradiance going into the cell. And this kind of structure is quite important to ensure the reliability, as I will show you in a couple of minutes. So having said that, we go into the degradation, which is the main part of this presentation. Ben has mentioned that heterojunction has been going on for a long time. And I've been working with heterojunction before Huasun for more than 12 years. And this is a technology that was invented in 1993 by people at Panasonic. Well, at the time it was Sanyo. And it was commercially introduced in the market in 1997. So it's been a long time. And the advantage that this gives to all of us, both the producers and the users, is that all of the failure mechanisms that happen with any new technology, sometimes they take a long time to be discovered because maybe the test that is available does not show that degradation. And over the years, some degradation methods have been happening, and they have been studied, understood, and then some things have been done in order to mitigate them. So we had EVA yellowing. You can see that mostly in modules produced from 2004 to around 2007. This was not a dangerous thing. It just reduced a little bit the yield, but it was chemically stable after yellowing the EVA, so it was not a big problem. We had some delamination when there was in production too much flux. This has been shown to be something that potentially is quite important. It was controlled very quickly after it was found out what was going on. There were hotspots that could happen because at the edge of the cell, there could be something called shunting, which means that the front and the back part of the cell would be electrically connected. Again, something that once it was understood, there was a mechanism to avoid it. Then we have several ways in which water vapor can cause corrosion in the cell or delamination, and the degradation that can happen with UV, and so on and so on. Today, we will focus on the problems that can happen with the ingress of water vapor in the laminate and with the degradation with the UV. We're going to focus on that specifically because basically everything else is very well controlled, and the ways in the production that can control all of the other mechanisms have been so well studied that it's basically state of the art. And we don't need to look at that in any depth because as long as the manufacturer knows what they're doing, they will control all the other forms of degradation. Let's go for that. Before we go, let me show you a couple of pictures for the yellowing. This you can see in the in-between space of the cells, and this module specifically has as well the delamination caused by the excess of flux. It is limited to the bus bars, so it was nothing that would really make the modules completely fail, but it was obviously not nice. And at the bottom, you can see the delamination that can start when you have an edge shunting, and that is more worrying because it may go further and then the module could fail altogether. One thing that has to be quite clear is that heterojunction, thanks to all of the long history, by the time that Panasonic was exiting the market, that happened at the end of last decade, it was a very, very stable and reliable platform. Just a couple of weeks ago, somebody, a researcher from the University of New South Wales in Australia, he quoted something like the Sanyo Panasonic modules are some of the most reliable and durable modules that they have ever tested. And this was of production methods that were in place maybe 1 decade ago, and it has kept on improving. The numbers for warranty cases that were published by Panasonic were something like less than 50 pieces per million of sold modules were a warranty case. And this not over the span of 1 or 2 years after introduction. No, this was decades after introduction. So really, really a very stable platform on top of which we as heterojunction manufacturer build on. So let's go for the UV degradation. We see here the quantic efficiency of a solar cell when you look at all of the wavelengths that arrive to the cell. And this is a shape where at the infrared here has a cutoff, a hard cutoff, because any wavelength, any light that comes with less energy will just not make any electron. Then it goes up rapidly, and then at the UV again goes down, either very dramatically with a UV cutoff film. This has been used in the industry for a long time for heterojunction. We still use it. Or a little bit less dramatically if you do nothing and just use EPE or EVE with high transmittance, or a very strange curve when you use what we are using today, which is called light conversion film. I will explain what's going on there in a minute. The point is light conversion film transforms some of the irradiance that comes in the ultraviolet spectrum into visible light. So that is why this hump happens. It's not that the light here in the ultraviolet suddenly gets absorbed by the cell. It is that the light that comes in this part of the spectrum gets transformed into visible light, which is in the part of the curve that is with a higher absorption curve value, and then we can use it very nicely. This characteristic gives a bit higher efficiency, but especially protects the cell from the UV irradiance. Let's look at what happens exactly. We have here a vertical line that shows the minimum energy necessary to break the bond between the silicon and the hydrogen. This chemical compound, silicon with hydrogen, is used in the passivation of the cell, not just for heterojunction, but for other technologies as well. So this is something that is valid as science for all of the most important cell technologies today. So when you have photons arriving with more energy, each one of them, than the minimum, they don't have to, but they may cause a break in the bond of silicon and hydrogen, and then it would make worse the passivation. And that is the main cause that we have found out in the industry as why there is degradation with UV light. If you look at this curve, it's showing the amount of photons coming with AM 1.5. This is the typical spectrum. It's a standard spectrum that happens maybe at midday in Spain in April, something like that. It's quite representative. And you see that there are photons coming with much more energy. They go from at a lower wavelength, at a smaller wavelength, and with less energy at a longer wavelength. So if we look at that curve, now I'm going to superpose what is the absorption with LCF. And this is the orange line now. And as you can see, we put away most of the ultraviolet light, especially the higher energy photons that are the most likely to cause damage to the cell. So this is the key point that either UV cutoff film or light conversion film has been doing in order to protect the cell from the harmful UV. This is quite similar to putting on sunscreen, let's say. Now, when we look at this method to avoid degradation, we need to look at how does it work over time. Because if you do a filtering, but like sunscreen, it goes away when you go into the water, it's not going to protect very long. Fortunately, this is not a new technology, not a new development, and it has been very thoroughly tested by the people who invented it and those who licensed it. So we have subjected this light conversion film to long-term testing that simulates the lifetime of the module, and the changes in the transmittance are so small that you don't see them in the curve on the left. You need to go to the curve on the right to see a very, very slight increase in transmittance at the important wavelength of about 350 nanometers. This means that the filtering still works very well. We do as well UV testing with EL imaging, and then you see that nothing is happening behind the scenes. So this is kind of a testing on the lab. And I want to show you what is the normal testing that is done. It's called UV testing. And the 3 times test of the ISE is the UV 180. We do that, not just the UV 180, but we do that with an accelerating factor of 5. This means that with higher intensity of UV, the effect of the degradation gets multiplied, and this multiplication factor is 5. So this simulates not the UV 180 on the module, but 180 multiplied by 5. And this is quite similar to the amount of UV that the module will get during the lifetime of it. And I want to show this. It shows a degradation at around 3% or less. It's nice. But I want to show at the same time the reality of the degradation. Because on the field, there is not only the UV like in the lab, but there are other things that happen in the real life, and they actually have an effect of sometimes recuperating some of this degradation. Because of that, we look at the reality with a keen eye, and fortunately, this method of preventing degradation has been used for many years now, and here we have an example that was installed in Osaka, in Japan, and the module that was put 8 years in operation showed after these 8 years a total degradation of 1.6%. Keep in mind, this is the total degradation. You cannot separate each degradation source. This is including UV, but not only UV. And this is 1.6% after 8 years. Look where Osaka is in the UV index. This is the black little circle that I have painted here between the yellow and the orange. And these are UV conditions that are similar to maybe Northern Africa or the south of Greece. So this means compared to European conditions, pretty high UV conditions, so quite strict. And we see that the reality is that for the lifetime of the module, this 3% degradation because of UV is realistic. It's actually even quite conservative. So this kind of approach that we have to look first at the source of the degradation, to implement scientifically proven methods of mitigation, and then to test both in the lab and in the reality is the way that we have to go about solving degradation and failure modes in modules. Now we're going to look at water vapor ingress. Here, I will not be able to go so deeply into the technology, into the science, because water vapor causes several problems in the cell, not just one. And what we have done is to mitigate the ingress of the water vapor itself. What we have done is to put sealing all around the laminate of the module to prevent the ingress of water vapor so that it will not be within the laminate. This is done with a material called PIB that is not invented by us, has been used in the industry and different industries for many years. And the water vapor penetration barrier has 100 times more effect to prevent the penetration of water than POE, which is the standard in the industry as the best barrier against water today. And this has 100 times more penetration resistance. So this is really a very good method to avoid water coming into the laminate. And we have decided to use it for heterojunction in order to avoid all of those problems, not just one by one those problems mitigating somehow in the cell, but really just avoiding the water altogether to be inside. If we test that in the lab, the DH, that means damp heat 6000, this is twice the value or twice the length and the difficulty of the test that is used in the long-term degradation test goes to DH 3000. When we do DH 6000, the degradation is again very controlled, something below 4%. So really very good values. This is way beyond the lifetime of the module. In order to validate that method, we have done a couple of things. The first one is more of a conceptual validation. We have put a cobalt chloride test paper. This is a paper that you may know from outside the photovoltaic. It turns colors when it has humidity around. So we put it in laminates and we subject those laminates to, again, very thorough damp heat testing. And as you can see, the color of the paper still stays within the blue because the water has not come inside of the lamination. If we look at that, then we see, okay, yeah, the water doesn't ingress. But we need to be even more thorough. So what we have done is we put the cell inside of this lamination with a PIB all around it. And we look at the EL, this means electroluminescence, after the very harsh testing. And we see that there is no visible change. This is quite important because if you look at the literature, if you look at all of the research institutes, you can see, pun intended, that under EL conditions, you see the degradation happening even before the actual number for the degradation is visible. Like you see that something is going on even before the cell shows a degradation value that is high. So this means that we have seen that this is a very good method to avoid degradation caused by water vapor. This includes the most typical corrosion, the lamination, even some PID effect. Now I want to show you something that is quite important because I told you before that heterojunction was a very strong and durable basis to do solar cells. But of course, we are not doing the same things that were done 4 or 5 years ago. We have been innovating. And I'm going to show you what we do to test any innovation step that we take. And I'm going to focus on the most important one, zero busbar, which came into mass production this year and is the key to reduce the cost and improve the efficiency of the heterojunction modules moving forward. Those of you who don't know zero busbar, the key point is that with super multi-busbar, soldering is done in these little white dots that you see in the third picture from left to right, which are called soldering pads. And then there is a machine that solders the ribbons. The ribbons are the little wires that connect all of the cells. They solder them on those points. Then this was better than before because you save a lot of silver. You only do the pads with more silver and not everything in the bus bar. But still, the soldering happens in specific points. And these, if the point of solder is failed, then you may have a problem with reliability over time. And the fact of soldering on those pads puts a lot of strain on the cell and they may break. So in order to get this done properly, you cannot decrease the thickness of the cell very much. So what the industry is doing for heterojunction is going to even thinner cells that require soldering that is more careful, and this is called zero busbar, in which the electrical contact of the ribbon, remember the thin wire that connects the cells, to the cell is done all over the surface of the cell. All over the surface of the ribbon, it is glued to the cell instead of being soldered at specific points. This is called zero busbar. I will not discuss today. You can find a lot of information in internet. Even we have done some webinars about it. But when you do something so radical like that, you change the interconnection of the cells and you glue them to the cell instead to the soldering pads, you need to test it because you could be causing damage to the surface of the cell, like the metal going into the TCO. You could be doing many things. So the two basic things to test are damp heat testing, again, because we need to see what happens when humidity is around, and TC, this is called temperature cycling testing, because this is what makes the connection of the ribbon to the cell be under stress, because it's like very hot, very cold, and the materials have different expansion and contraction numbers and characteristics. So the connection of the cell and the ribbon could get worse over time. And those we test, and we only satisfy when the values for zero busbar are comparable to the values of the technology before, super multi-busbar. And with zero busbar, we test here both with the silver paste and with the more practical silver with copper paste. And the values are very, very good. Additional to that, we do all of the other reliability tests, such as mechanical load, you see on the bottom left, or the very complicated test that combines UV, temperature cycle, and humidity freeze. You see that on the right bottom. And those are really quite strained on the module. And the values of degradation, you see 0.something%, really, really very low degradation values. That is how we validate any new development that we put into mass production. And with that, I want to finish with a bit of an outlook. Remember, heterojunction has been going on for many years. It has shown on the reality and in the lab that it is a very, very durable module. We as Huasun do that, not just based on the structure, but making sure that the most important points, UV and humidity ingress, are very specifically and very well treated so that we block UV and we block humidity. And every time that something new happens in the cell or in the module technology, we do a very strict battery of testing to ensure that that very good platform stays very good or even improves more. And that is why we think that heterojunction moving forward is going to be the key technology, because that very durable and very well protected module and cell structure is going to be what is the substrate for tandem heterojunction with perovskite in 2 or 3 years from now, and that will require very good isolation from the environment, such as the isolation that heterojunction is giving. With this, I've finished. Thank you very much. Ben, I give it back to you.
Thank you very much for that, Christian. That was really interesting and very insightful. Gives us some pretty good insights there into HJT durability. So thank you. A few questions coming in. Yeah, I mean, I think you mentioned early on in the presentation about Panasonic having been a sort of key player early on in the life of HJT. How similar is the heterojunction that Panasonic implemented to what you, Huasun, are doing today?
The basic of the technology is quite similar. So the thing that makes heterojunction special is the amorphous silicon passivation of the wafer, and that remains the same. What is different is that Panasonic, as far as I know, was using only amorphous silicon for all of the layers on top of the cell, and heterojunction 3.0, which is the standard in this industry right now, and we use it, has amorphous silicon next to the wafer, but after that, we have microcrystalline silicon. That is a difference. The second difference is very subtle, is that when I say amorphous silicon and microcrystalline silicon, in reality, there are different layers that are very slightly different from each other, but that's all inside of secret manufacturing methods that differ from one to the other. I cannot comment on that. And the other difference is related to the surface of the cell, where we use a different TCO with less indium, because as you may know, indium is relatively rare, and as an industry, we're reducing the amount of indium used. And the metallization. Back then, the metallization was done with silver paste that was basically pure silver, and a lot of it. And most of the cost reduction has happened reducing the amount of silver on the cell. And that is the main difference when you look at one cell or the other from the past to the present. Actually, you know what? Let me see here. I don't have it here now. Yes, it's here. I can show you actually. So this here, I hope it's kind of visible. It's a heterojunction cell from 2004 from Panasonic. It's a laminate with no bifaciality. And this here is, it's sometimes not visible, super multi-bus bar from us, let's say last year. And this here, it is with 0 bus bar as of today. And if I turn it around, you see basically no difference, right? Yeah, then you can see it. The effects make it difficult. But if you look at that, I'm gonna remove the, for a moment, I cannot do it easily. And I'm gonna put no virtual background, so you see my office. Yeah, you see now my office on the back, but it's useful. So this is the cell with 0 bus bar right now, and this is the other cell. And as you can see, the metallization is very, very different. And if you could see the backside of this one, it has a lot of added metallization. So that is the main difference.
Thank you very much. Question here was relating actually to some coverage that we've recently run on PVTECH. We ran an interview with a leading researcher at the University of New South Wales in Australia, talking about degradation, particularly of heterojunction and TOPCon cells. I mean, it was quite a wide-ranging interview. I definitely suggest looking it up because it was a really interesting read. But one of the points he made was that at the moment, heterojunction modules are produced largely by, a few players such as Huasun, and that, on the whole, those established players have got a pretty good track record on degradation and reliability, but for various reasons, but because presumably the sort of testing regimes that you have, and also the fact that you have a fairly sort of conservative bill of materials, which enables you to offer certain guarantees about the the durability of your products. But and I think in my intro I mentioned that there was the likelihood of much more heterojunction modules being produced in the coming years, which perhaps indicates other players are going to come into this field, perhaps who don't have the same sort of long track record that companies such as Huasun have. I mean, how much of a risk do you think there is that new players coming into this field won't have that same sort of long view that you're able to take, or indeed the the sort of necessary testing and other regimes in place to ensure that their products are going to perform as expected over their sort of expected lifetime?
So that's a good question. It's kind of almost philosophical, right? I don't want to do any kind of fear mongering, because I think it's not fair to all of the colleagues who actually do a very good job. So the point here is that heterojunction itself, you don't just wake up one morning and do heterojunction and suddenly you have 10 gigawatt of heterojunction production, right? So you go to manufacturers of production lines for cells and for modules, you talk to them, and they have a lot of know-how. And they know what works, what doesn't work to a great extent. So a manufacturer that will enter the market will not just come out of the blue, and will have already all of the know-how of all of their suppliers in order how to do heterojunction modules well. This is how useful it is to have an original platform that is so reliable, because everybody who is selling you the machines knows and tells you, yeah, you need to do this, otherwise they degrade. The point here is that all of the technologies happen to have a similar approach. If you buy TOPCon modules from any supplier, you need to be equally vigilant, right? I remember, I think the presentation was not only about heterojunction. I've seen the same guy doing a more generic presentation as well with TOPCon. And any technology that uses, that gets very high efficiency, typically is doing a very sophisticated passivation of the cell, because that word passivation is what makes the difference between a cell that works well and a cell that works very well. And those sophisticated passivation layers are typically the ones that may get attacked by the environment and cause degradation. This is just a very general approach to it. So we all, with high efficiency, are trying to mitigate the same things, generally speaking. I actually see that those who will do heterojunction, as long as the approach is a conservative bill of materials that actually prevents the danger from happening, filtering out water, UV, I think that is the most safe option to go for it. Because if you are trying to solve the effect of the water ingress, you need to solve all of the problems that happen when water is inside. And some of them are not well understood, even for TOPCon. Then you are trying to whack-a-mole all of these things, right? Oh, this problem happens because water combined with acetic acid corrosion. Oh, boom. Oh, this is with natrium here. Oh, another layer on top of the cell to avoid the natrium. Oh, another for the acetic acid. Oh, now we cannot use EVA because of this. Oh, now we have to change this. This is a whack-a-mole, and going to a conservative bill of materials means that you avoid the ingress of the water, and then you kind of, okay, no water vapor inside. So all of these three effects we tested, they are not happening, or to such a small degree that we don't care. In that sense, I think heterojunction is actually more safe. But you need, as a purchaser, to make sure that the bill of materials is there. For us, it's kind of funny because it's so simple. We do UV control with UV cutoff film or LCF, light conversion film, and there is basically one supplier of that. So when you look at all of the materials that are important for the reliability, you look at the edge sealing, which is made by us, always the same, and you look at the encapsulation, which in this case is always the same, and the cell, which is ours, always the same. So it's very simple bill of materials, and I think everybody who joins the industry will have a similarly simple bill of materials, which is an advantage of heterojunction in that sense. You don't have 20 suppliers of POE, EPE, extruded combinations like with TOPCon.
Thank you. Had a couple of questions which I'll try and sort of wrap into one about details of your testing practices. One asking if you undertake any testing in very hot conditions, so ambient temperatures of more than 48 degrees C for periods of, say, 3 to 4 months. Also one about your damp heat testing regime and the length of time that you do that for. The questioner said 8,000 hours, I guess that would be a sort of suggested length to kind of really understand what goes on. But anyway, I may have misunderstood the question there, but clearly the question is about, how long you do these tests for. So any more detail you're able to give on that would be great.
So about the hot temperature we have right now, we installed last year a testing site in Saudi Arabia, which is not the coldest place in the world. It's performing very well, but I am a friend of wait and see in order to give you an actual real feedback about how the real life modules are working. We expect we don't see any chemical or electrical process that should happen at 50 degrees that doesn't happen at 40 degrees, generally speaking. The UV load, of course, is a bit different in those areas. But about the DH, we did DH6000, which is already twice the normal. The normal, I don't mean the normal IC, I mean the normal long-term testing. And as you can see here for the results of the DH, they stabilize quite nicely around there. Of course, we could try and do 8,000 or 10,000 or I don't know, something crazy. But the people at the lab, they just don't like to do tests that don't relate to the actual lifetime of the module. So if a customer has a project of 100 megawatt and they want to do that test, we provide the modules and they can go to any lab and do them testing for DH 10,000 and let us know what happens. And if something strange happens, we'll look at it.
Great, thank you. Couple of questions about TOPCon. I mean, I guess arguably heterojunction and TOPCon are kind of talked about almost in the same breath these days as the sort of dominant technologies that we're likely to see, and are already really seeing that this year and over the next few years. Relative to TOPCon, would you expect heterojunction to have lower degradation, and the humidity degradation in heterojunction, is it the same as that seen in TOPCon modules?
So for the reality, I think it's going to be a coin toss up which one of the modules will show lower degradation compared to the other. Generally speaking, heterojunction should have lower degradation in generic average conditions, or if you average modules installed everywhere and you see the degradation of each one of them, it should be a bit lower with heterojunction. But not fundamentally. Is more related to things like that I didn't talk about today. Like heterojunction has a more flexible cell, which is very immune to cracks. So that is one of the points that it was not talked about today. And I have customers who only focus on micro cracks on the cells because they have so many problems with that. And that's related to TOPCon or other technologies having grooves, like laser grooves made in the wafer. And those are the starting points of cracks when they are subject to mechanical load. And heterojunction is just on top of the surface. You do everything on the surface. That's why they get more flexible, they're thinner. So in general, I would say lower degradation is to be expected, especially in Europe, where snow load maybe happens, and UV is anyway very low. The second part of your question, I forgot, so please ask again.
It was, sorry, just remind myself. Yeah, it was about humidity degradation in heterojunction and whether that was the same.
Yes, it has seemed to be more strict. According to what has been tested, apparently humidity is more of a issue for heterojunction compared to TOPCon. Yes, that's state of the art. Maybe not with the first heterojunction, because remember, we have modules installed in very humid Japan for 25 years with EVA as encapsulant and backsheet, and they're perfectly fine, right? Most of them like 99.999, whatever percentage, like no claims. So historically speaking, no, but with the current generation of heterojunction, it seems that it's a little bit more sensitive. So yeah, it seems to be related to the use of microcrystalline or polycrystalline on the rear side, which is something that TOPCon makes. It's part of the TOPCon structure, but it seems to be a bit more with heterojunction.
Good. Well, we're nearly out of time. I just wanted in my introduction, I sort of talked about how the heterojunction was sort of moving from the rooftop to the field, if you like, from rooftop applications to utility scale. I mean, in terms of the sort of ongoing monitoring of the performance of heterojunction in those kind of applications, large projects, whether that has any implications for you as a producer of heterojunction, or indeed companies that are installing these in the field, sort of gathering real world data, understanding how they perform in those sorts of situations over time.
Yeah, this is I think this is an interesting topic that deserves actually a webinar by itself. So we have a characterization of the technologies, and the most basic numbers are like low light performance, temperature coefficient, bifaciality, right? So those are the three things that define the performance. And most companies just put them into PAM files and people simulate with PVCs. The issues begin that simulation was not originally conceived for heterojunction technology of the cell. So it's already a little bit tricky. But any simulation is tricky, and it's very tricky and way too easy to do kind of tricks with PAM files. I forgot the light IAM incident angle modifier, and it's too easy to do some kind of trick with those, even with third-party reports, and I hate that. What I think is the next step is that people will install or should install in representative climates and situations the modules with a certain PAM file and then validate the simulation in some way. We are trying to strive in that direction. We have many, I think, I don't know, 5, 6, 7 sites where mostly customers of us have installed testing sites, and then they compare TOPCon with heterojunction, and they give about what is expected, maybe 2% in Spanish climate conditions, maybe 4% in Saudi climate conditions, gap of performance compared to TOPCon, a bit more compared to PERC, like 6% or something like that. But those are specific cases that are not scientifically so well controlled that I would say they are always like that. So I would welcome every customer who wants to test that and to check that to contact us, and we help each other to set up some kind of testing for them to actually control all of the things that may be manipulated if you have to trust a third party to do it. I don't trust anybody to do it. Honestly, if you ask me to set up a testing site that wants to get these results, I will manage to do it and you will not see what I did and you get those results. So if you guys listening are EPCs or developers who want to actually test for yourself and don't want to trust manufacturers, third parties, talk to us and we'll set up something where you control those things and you don't get fooled.
Great. And who knows, maybe we can have another webinar to talk through some of the results from that. That would be good. Thank you. Great. Well, we are out of time. So thank you very much, Christian. Today's presentation, a couple of you have asked about this. Yes, it will be sent out after the webinar, so keep an eye out for that. The full webinar will also be available in a couple of days also on PVTECH, so you can listen back to anything that you've heard today on that. So yeah, so that's it really. All that remains for me is to say a massive thanks to Huasun for sponsoring the webinar today, and of course Christian again for his expert guidance through this topic. Thank you, Christian. From me and all the team at PVTECH, many thanks for tuning in. Have a very good rest of your day. Thank you and goodbye.
Thank you, everyone. Thank you, Ben. Bye.